Okay, so we start 1 hour question plus discussions, and we will use the same rule. So if you have a question, which is a new question, you raise your hand. If you have a follow-up, you raise your finger. And we will start with Neil, who had a question, I think, for Faye, right?
Yeah. So you showed us this, well, Sumati is here as well, but you showed us this amazing formula, which is that the sum cancel exactly the certain types of causal networks. Did you get this? It sounds very implausible. E to the IS is a phase, and you're adding it up on the circle. You'd think the sum went like a random walk.
Yeah.
So,
Okay. Yeah. Let me do that then. I think Sumati will do a much more sophisticated thing. So this is just a quick and dirty way to see that. So the basic idea is that these KR orders are these randomly generated tripartite objects. So
Sorry,
you
could you
have,
please use the microphone?
yeah, so you have n over 4 elements down here, n over 2 elements here, and n over 4 over here. Okay, and we want to calculate the sum over all things like this, where the class of things I'm going to sum over are, I take this tripartite structure and I put a link between two elements in either 2 elements in these 2 layers or 2 elements in these 2 layers with probability 1/2. That's it. So a link is either there or not there with probability 1/2. And we can just count how many. So this is the set of that's how I define a KR order, right? It's anything that you can get from this process. And remember that the action, so I'm going to say the action is equal to some number, let me call it, I don't know, alpha, times n, and then minus n1 plus n2. I think there might be a 2 here. Yeah, and a 4 here. These minus 2 and 3, something like that. Okay. Okay, our orders e to the is of c. Okay, so n is fixed. That's just the rule, right? So s is equal to, for every single one, n is the same. So n is the same. So it's just going to come out as a factor, just a total phase, right? But what's n1 is the number of links. And the number of links is k. So the total number of links that you could have is combinatorics. We did this course. What was it called? Permutations and combinations, and it's all just counting numbers of things. It was a terrible course. I mean, it was a great course. I was terrible at it. Okay, so you're going to have to help me. All right, so how many links could there possibly be? That's when they're all there. So that has each one of these has n over 2, and there are n over 4 of them. Right, so that's how many links there could be here. And then there's the same on the top, so it's just 2. So that's the max. So I'm going to call that n max. Right, so that's the total, that's the maximum number of links there could be there, right? So this thing becomes e to the I alpha n, that's the same for them all, sum over, and so this is just k. It's the number, I'm going to call the number of links, I'm going to call that k, right? So there'll be some number of links k. The maximum number that k can be is n max, and the smallest it can be is 0 if there are just no links, right? It's just no relations at all. Now, what's n2? N2 is the number of cardinality 3 chains. And basically you never get those. The probability of those is in the limit when n, so I'm going to calculate the limit as n goes to infinity. The probability of getting any of those is 0 as n goes to infinity, because you'd have to have a point here and a point here with only one element between them. But that just won't happen because, there's bound, this is below a half of them randomly chosen. This is above a half of them randomly chosen. And you're bound to get, quite a lot of elements between them. So you basically get none of these. So this is essentially 0. And this is also essentially 0. So the only thing that matters is the link, the number of links. No. Okay, so you get this. So it's a sum over the number of links, and the action only depends on the number of links. So it's e to the I minus 2 alpha k. But each number k can happen in you can get a KR order with k links in many different ways, right? So that's so k has to be 0 to n max, and it's just n max choose k, because n max is the number of possible links, and you just choose k of them, right? That's how you get k elements. So the number of causal sets with that number k links is this. So that's to the I alpha n. This is 1 plus e to the minus 2 alpha I k to the n max. Oh, sorry. Get rid of the k, right? So let's take out a factor of e to the I alpha n, e to the minus I alpha, and then you get cosine, twice cosine e to the I alpha. Is that it? Yeah. Oh, sorry, that's a cosine. Yes, cosine of alpha. Yeah. So that's this bound on alpha. So alpha has to be such that, so we need cosine of alpha to be less than a half, right? So there's some bound on it, but it's not a fine tuning, but it's some condition on alpha. So if that's true, then n max goes like n squared. So as n goes to infinity, this is going to 0. That's it.
Follow up by Renata.
Yeah, so school doesn't say, well, I get tons of terms, of course, that are really nasty and beyond, vastly beyond exponential growth. So I guess not such nice simplification.
Absolutely. Yes. There are lots and lots of ways to be non-manifold like, and those classes can also have super exponential growth in them, in the numbers.
You do know that the dominant ones, because all the layered sets, they all go like 2 to the n squared upon 4 times some number, and as the layers increase, that number becomes smaller. But so n squared is a dominant thing, which you can show none of those contribute. So things that are subleading to n squared but are still super exponential. Something like an n log n kind of contribution. We don't know anything about those.
But that could be,
They could be.
that could be funny powers, we don't, I don't understand.
Yeah, I mean, there's anything between n squared and n, but once you come down to n, then you're okay.
Yeah, you're fine.
Basically,
It's a long
okay.
way down to end.
Yes. Yeah, so we don't know anything about that range of possible things that could be there.
By Roberto.
Maybe a very superficial. I seem to remember that in CDT we will have some phases where the universe looks like a pancake. And this reminds me a little bit of that. So is there a connection? And
No, there is no connection because we have really exponentially many at deep water. It's not a, but it's another, entropic, it's an entropic type thing that maximizes a certain number combinatorially just by,
but that seems to be also the case for her.
Yeah, I mean, for example, you could definitely have.
It could be some subsector, but I mean, these are vastly many. Still in our pancake phase, still things scale exponentially. So the entropic arguments will be different ones. They may maximize the available entropy by a similar kind of.
But you have, in order to, but your phase is characterized by certain choices of parameters.
Yeah.
Whereas here it seems that this is
No,
full stop.
Yeah. With us, it depends, of course, where you are in phase space.
Yes.
You can see, of course, in our ends are, of course, different ends. They come from continuous things, and they are not all independent. They obey, Sommerfeld conditions. So they're totally different animals, our NIs. So
What is your comment?
I'm just summarizing what Renata said. So the number of CDTs grows like it's exponential. So it grows like e to the n. So our problem, our cosmological constant problem or entropic problem is orders of magnitude worse. It's, yeah.
Is there any more follow-up on this point? Otherwise, we have Bo with a new question.
Yeah, it's a sensorial question, but still about large N. My sort of impact on the talk, there was first was the matrix models where large N is important for finding double scaling in etc. And then somehow in my mind at least I lost track of large N. But I suppose it's there for the other.
So in the simpler tensor models, the straightforward combinatorial generalization of the matrix models, but where you just stick to combinatorics, there is a similar n. It's exactly the size of the index set for the tensor, and there is a larger n expansion that is not in different topologies. It's not that different topologies are organized at different orders of n, but there is a large n expansion, and what people have shown, and there is then refinement of that expansion in terms of double scaling, triple scaling limits, and so on. But what happens in the large n expansion is that a particular subclass of triangulations of the sphere, or planar more generally, is dominant. Not any triangulation of the sphere, so it's not just every sphere is there, but a subclass. This subclass is a very special one. I mean, mathematically nice, physically probably not, which is so-called melonic diagrams. And I don't know where you come from, but if you come from, I don't know, if you want to link with what happens with the SYK model, is the sort of diagrams that appear there in the UV. And that was the starting point of the application of all these tensorial techniques in that context. The second subclass of models that I mentioned at the beginning. So there is control over the large N expansion, but from the point of view of topologies and probably gravitational physics, it doesn't appear like the relevant regime for extracting effective continuum physics. At least not in the straightforward way of saying, the typical triangulation you get in this regime looks like a nice, triangulation of the sphere. Because these ones, if you use the graph distance, so if you treat them as equilateral triangulations, then the spectral dimension is that of branch polymers, the Hausdorff dimension is that of branch polymers. So from that point of view, they don't look particularly nice. Exactly. So you can go for double scaling limits, triple scaling limits by introducing other parameters. You can get out of that simple class of diagrams, but also the other class of diagrams that you get by the multiple scaling limits that have been considered don't look particularly nice from the geometric point of view. So this is what I think this subject is. Now for things, well, there are two attitudes you can take. You may hope or expect that adding the quantum geometry data changes the story. So you don't rely anymore on the combinatorics, and even your notion of metric on the lattice is not just the graph distance. Could be. There are counter arguments to this possibility, but it's a possibility. The other is that maybe it's the expectation that the relevant physical regime or the relevant interesting gravitational space-time physics has to be extracted in a phase in which the typical triangulations are themselves nice triangulations of a space. That may not be the case. These are two attitudes that people are taking. Of course, some people are taking the attitude that, well, this shows that this class of models, and unless you do something radically different, they just cannot work. That's fine.
Yeah, no, just you also fit into the discussion, of course, how does the configuration space grow as a function of n?
Mm-hmm.
So modularity is also super exponential, but in the subsectors, which you mentioned, which you call the Malonic diagrams, what is the growth there?
In that case, you can also resum the Malonic series in the limit. You can count.
Can you resum it? I'm asking, it's also super exponential?
I don't remember the exact. No, I think it's exponential. I think, but I don't remember exactly. You can actually take. I think you get exactly the typical branch polymer counting, and that you have in your phase for these models, for the ones for the Euclidean DT.
Well, of course, you can resum often by just rearranging.
So
Sample, but then you will get ambiguities.
they're not summable. You can go to a continuum limit by tuning the parameter appropriately to. Yes. But for these models in this larger regime is literally like the Euclidean dynamical triangulations in the branch polymer phase. There.
The outcomes like that doesn't make a lot of sense. It's a very strongly attractive pathology, as we know.
Yeah, that's an example of the third attitude that you could take.
The bad histories? That's a voice. Not the nasty one, but we have to get rid of the press.
Okay, we just call them bad.
Yeah, it's not.
Is there any?
If I can just add something, I mean, of course, the problem of extracting interesting physics is the more interesting and also the more difficult one. But if you first just ask if you can control this sum over diagrams in particular regimes, well, and even going beyond this Malonic phase mathematically, well, then for models in which you have a more interesting RG flow, because they are proper field theories with a non-trivial domain and so on, both things have been shown. I mean, the 3D model that have shown being perturbatively normalizable So you don't resum anything, but you can show that that perturbative expansion is well defined, is under control. Another thing that has been shown for four-dimensional extensions of that model, not the full-blown quantum gravity ones, but models which are in 4D, is that the RG flow can bring you out to the melonically dominated diagrams. Again, whether that changes really drastically the fact that the typical triangulations still don't look nice enough, that I don't know. But
if there is
Your sprinkling on Minkowski, it was pretty dramatic, and many of the points were quite far away, as you pointed out. And so what does that imply for the locality of interactions that might come out of in a continuum limit on the manifold like ones? Are they become rarer as you go, or do you get non-local interactions?
That's like what used to be called the $64 million question, or it's probably now the $64 billion question with inflation. So yeah, so locality, non-locality, how does the local physics that we know emerge from something so non-local like this? And can we get phenomenology from the non-local? Can we tame it so that we get local physics, but still have some non-local phenomenology? Those are the questions that we're struggling with all the time. So it is very non-local, and in some sense, the non-locality is already there in Lorentzian geometry. It's this feature of Lorentzian geometry because there are the null directions. The distance between any 2 points on a null geodesic is 0. So, the locus of the set of points which are one Planck time away from any given point is a whole 3-dimensional hyperboloid that asymptotes to the light cone. So the non-locality is kind of, if it's not already in Lorentzian geometry, it's sort of on the verge of being non-local, and the discreteness kind of tips you over the edge into the non-locality revealing itself. So for a long time, we were very unsure about whether we could define a D'Alembert for a scalar field on a causal set. Because of the non-locality, there's no difference between in a particular frame, some nearest neighbors to the point at which you want to calculate D'Alembert look close, they're in that frame. But some look very far away. They're down the light cone, but they're all on the same footing in physically. So how do you cope with that? I mean, if you wanted a finitary version of a differential operator, then you're going to use nearest, differences between the field values at nearest neighbors and next nearest neighbors. But you have so many nearest neighbors and so many next nearest neighbors, and you have to treat them all on the same footing. How are you going to do that? And how's that going to give you a local answer? So we didn't know how to do that for a long time. And then Raphael realized that you could do it by a judicious choice of coefficient. So essentially you can define D'Alembert for a causal set, for a scalar field on a causal set at a particular point which is Lorentz invariant. You sum the values of the field over all of the nearest neighbors, and you weight that with a particular number and add it to the value of the field or subtract it from the value of the field at the point. And then you do that for the next nearest neighbor, and then you do it to the next nearest neighbors. And the magic of those particular coefficients that you choose gives you something which in the continuum limit gives you the D'Alembert acting on the scalar field. So
specific numbers.
Specific numbers, and those numbers are the numbers that appear in the action. So the story that I didn't tell you about where those numbers came from, those particular numbers that appear in the action, they come from that D'Alembert, that whole D'Alembert story. So so we have something which is quasi-local. So if the the sprinkling density is high enough, then you get something which is close to the local value. I mean, the continuum D'Alembert of the field, but there are corrections to it. So we're working on whether one can get phenomenology from that, which would be it would be non-local phenomenology. So it's
That just really, in some sense, gives you the kinetic energy part. Do we ever actually have to be dialed, constructed carefully to make them local too?
I don't know the answer to that question. Yeah.
Is there any entropic factors that there are more local ones than there are wildly non-local ones? Or are they sort of entropically the same?
They're all on the same footing. The Lorentz invariance demands that they're all on the same footing, and it's a magical cancellation that occurs for the value. So what's actually happening in the calculation, if you look at for specific examples of functions where you actually do the calculation of what this D'Alembert is that the calculation itself picks out a frame in which the scalar field is slowly varying. So, if you take some scalar field, boost it a lot, then in that frame, it can look like it's it's Transplanckian. It has its variations are typically on scales smaller than the Planck scale. But that doesn't matter in a Lorentz invariant theory because so long as there's some frame in which it's slowly varying, then it's a well-defined, physically meaningful field. So what the calculation does is it's formally Lorentz invariant, but when you actually calculate it, it's actually picking out the frame in which the field itself chooses the frame for you in which the derivatives are being calculated. So I didn't answer your question about the interactions, but yeah, I don't know the answer to that.
Renata, is there any follow-up? Well, actually, I can just have a small follow-up on this because I think a few years ago I read this paper by Sorkin. It's the one basically where he considered this, let's say, maybe toy model with a scalar field, and he gets like some kinetic operator where you have a box plus no localities of the type like square root of box and logarithm of box, I think. Okay, these were the type of no localities that I think you were referring to.
Yeah, Raphael and collaborators looked at a continuum, a phenomenological continuum model based on this causal set D'Alembertian, and studied its stability, the stability of the propagation. So it's stable in 2D. It's unstable in 4D. So yeah, so attempts have been made to look at a non-local physics in the continuum based on this. So,
it may be that in principle, if you think about effective Lagrangian for gravity, you will have these no localities of this type. Also, the interactions might get affected because you will have some covariant Lagrangian, let's say, in terms of curvature. And once you expand, you will have propagator which get this no locality and interactions as well, I guess. So maybe
very little has been done on that. It's an open field, open question.
Yeah, thanks. There is Renata.
Yeah, so talking a lot about general principles of physical theories, in particular field theories, locality, causality, renormalizability, unitarity. So now you're working with these gauge field theories, which are auxiliary, I would think of as auxiliary and not primarily physical theories. So question number one, why should any of what I like to my physical point of view theories to obey, why should they be satisfied, or do they need to be satisfied in your auxiliary theory? And the second step is then, well, how if they do or don't, what does it imply for the physical, like the quantum gravity theory you might get out, you want to get out of there? Does it vary? How does the renormalizability or unitarity of one imply same property for the other?
So this is more of a question for the later panel discussion in the afternoon, but it directly ties to what I said. So sure. Okay. Let me first say that personally, at least, I don't speak for the community, but I do not see these theories as auxiliary or the unphysical ones. For me, these are the physical formulation of the theory. Now,
But
and
they don't live in space time.
yes, exactly.
Somewhere.
They are the formulation of the fundamental degrees of freedom of the theory, which do not live in space-time. And it's the other way around. It's the effective physics that we know on space-time, which is indeed, not auxiliary because we use it. So it's actually, the basis of physics, but it's the effective, approximate description of the real story. But your question that does not really rely too much on the perspective, doesn't depend too much on the perspective. Technically, but also from this conceptual point of view, I do not expect them to satisfy the usual principles of quantum field theory, all of them at least. Definitely, I don't expect any sort of unitarity.
You don't have.
Because I have first of all, because I have no idea how to formulate it in absence of a temporal direction. If there is a formulation that somehow is maybe more abstract and it has to do with just the partition function or the transition amplitude of the theory, then maybe I will check on a case-by-case basis if that more abstract definition is satisfied by specific models. But I don't have any general expectation that they had to be unitary in any standard sense. Quite the contrary. They are non-local from the point of view of the domain in which they are defined, in the sense that I tried to explain. And from the point of view of the effective space-time that has to be reconstructed, if I'm serious about the first statement, that these are the fundamental formulation, the rest is reconstructed, and the usual principles of locality and a number of other symmetries and so on will also be only approximate. So yes, I mean, these theories are field theories for a number of features they have which are apparent and they are shared with the usual field theory, but I do not expect them or require them to satisfy all the principles of quantum field theory.
So people have, so especially more recent times, use them not for gravity, that's moved away from gravity, like the French crowd, but investigated the theories for specific gauge groups. So typically what happens then, I mean, which of these general properties are satisfied for the field theory, maybe none, some, can you say something?
So people have investigated, not myself, but a number of people in the community have investigated to what extent these tensorial field theories satisfy the Whiteman axioms. And they had to reformulate them in a certain way, and they checked. They were looking for, in particular, of course, reflection positivity that you were thinking of. They have tried, and but again, my understanding is that there's no conclusive result of whether they do satisfy it or not, because there's no consensus on what is the proper formulation of the axiom in this case. And that's my understanding.
Is there a follow-up or any question?
It's a question.
Because there was first Sumati, then Paolo, and then Alessio.
Comes from, following the question I asked, I'm trying to understand. First of all, the domain that you have for your matrix values that I take.
Yes.
It's of course very suggestive in some ways, because if you took that to be the indices of the causal set, that's also a possibility in your approach. You could have each of those entries as elements of the causal set, and then you're constructing a theory from that. Because very often we in fact just write, the value 5x is 5j, and it's very similar in this way. But then you have these these functions that could have many arguments, right? And that's the kind of traces that you're taking. So, and that, I mean, that sort of links to this question, naive question, which I think maybe if you can answer and explain to me, that would be helpful. How do you, because you have just this K matrix, this script K thing that you had, which was just either full of delta functions or something, right? Which were matching, that helps you take the trace. So there's no background structure, there's no Lorentzian structure. I'm not able to understand exactly how you go from this theory to something that tells you how to patch things up. Are you simply saying that in your theory, you're going to patch up all of these local pieces in any which way you want to without any constraints on them, or?
With the only constraint about the gluing coming from the propagator that will tell you which argument has to be identified with which one. It doesn't fit the combinatorics because that's local, and so you can start gluing with propagators along.
But that gluing only allow, I mean, it's basically just Kronecker deltas, right? So
Sorry?
they're just Kronecker deltas that you're using to glue.
Well, for the simplest models, they're just Kronecker deltas, but the propagator in other models is more complicated than that.
So is that related at all to geometry that you will eventually, for the choice of that propagator seems to be
the choice of
information about the eventual geometry. It doesn't have to be an actual manifold, but there's
so the choice of propagator, just like the choice of interaction kernel, which function enters the interaction term, beyond the combinatorics, will determine the specific form of the Feynman amplitudes. If you want the specific form of the lattice gravity path integral, you get there. So that if you could say it will fix for you the choice of action that appears in the exponential part of that amplitude and the measure. So prescribing those elements will amount to prescribing a certain discretization of gravity if that's.
I want to just start in higher dimensions, for example, and say that I want to be able to reproduce the set of all Lorentzian space-times, something like this.
Yes, I'm talking about Lorentzian. I'm talking about Lorentzian path integrals, not necessarily Euclidean ones.
In any dimension.
Yeah.
So there, this gluing function, is it? I mean, maybe I just don't see how global.
So the construction procedure can work in reverse with some ambiguities. I can choose a certain spin foam amplitude or lattice path integral. So for the whole space-time triangulation, so to speak, I mean, the whole lattice. And in order to reconstruct what is the groove field theory that produces that, I have to be able to sort of factorize the expression for the amplitude for the lattice path integral into components associated to the individual four simplices or four-dimensional cells if you have a different combinatorics, and amplitudes that have to do with the lower dimensional cells, which have to do with the gluing.
That must not be the universal for all geometries.
And the geometries are the configurations I put on the lattice. The dynamics for a given geometry on a lattice is the amplitude. To the extent in which I can find easily this factorized or decomposed expression for the amplitude, I will immediately determine what is the kinetic term and interaction term of the groove field theory that will produce that. Which geometries will be allowed to be included? Well, of course, it depends on the amplitude, because it could be such that some geometries have zero amplitude, and so they're simply not there.
Right, so that's the basic question.
And it has to do, that becomes, okay, so it's the question about the amplitude, and then of course it has to do with the range of integration for the variables I have either at the groove field theory level or at the level of the amplitudes. I can decide that I exclude any edge length above a certain value or below a certain value. Or it follows from the algebraic structure of the group. It's partially a choice, partially coming from the mathematics of the theory. But the construction procedure, what I said, I mean, there is a correspondence with some ambiguity that I can tell you where they come from between a certain choice of action of the groove field theory and a certain amplitude at the Feynman expansion level. You can use it one way or the other, depending where you come from. The ambiguities have to do, first of all, that there are many different ways of discretizing a continuum action. If that's your motivation for choosing an amplitude, it goes in different ways. But then even after you have a certain amplitude, first of all, that's only the perturbative regime, and it doesn't totally fix the field theory. Second, at the field theory level, you can do field redefinitions. So you get a certain action for a groove field theory following a certain Feynman rules, but then you can always redefine your fields and move around terms in the action, even maintaining the same amplitudes. So these are the sort of ambiguity you still have. But in general, for model building, we tend to rely a lot on this correspondence.
Then you slightly rephrase what you're saying. Lorentzian structures are probably the same, and whatever you can tell your amplitudes is just local rules.
Yes, from this point of view, you do not know if these piecewise flat geometries you have also allow you to have a nice, just like you cannot ensure in the construction that there is a nice topology, like it's a manifold with no singularities at the topological level. There's no guarantee that this local construction allow you to assign to the full lattice a nice Lorentzian piecewise flat metric. There could be mismatch of light cones, so there would be singularities in the causal structure and so on. Of course, this, yeah, I mean, that's basically the thing.
It's true that you will get more stuff.
Mm-hmm. Yeah.
Except the question
And
is,
you're used to dealing with more stuff.
we're used to that.
That does screw you up. That's the problem.
No. But the question is, and I guess I'm still looking to us to see how from that local structure. I mean, if I have a manifold, I know how to do simultaneous decomposition, do piecewise linearization, and I know that, stuff, curvature is sitting at corners, and you could, have a nice way of understanding what curvature is. Here, because you're starting off without any of that structure, I'm just wondering how you encode it you're stitching things up, but what you're stitching up is not very clear to me that you will get the space of all possible Lorentzian geometries.
No, you will get those, but many, many more.
Yeah, maybe you can get more, but I mean.
Yeah, that's exactly the point. Exactly because I don't put more global conditions. By this local construction, you get more configurations, not less. But I can give you an example. If I wanted to obtain, and we were trying, if I wanted to obtain not only local causal structure reasonably well defined, or gluing of local structure reasonably well defined, but I wanted to obtain something more global, like a given ordering, like in causal dynamical triangulation, which is in the standard formulation a global constraint on the triangulation. That's basically. Okay, I was about to say impossible, but it's extremely hard to impose in this Feynmanological level in terms of local gluing conditions, because it's not a local condition, it's a global one. And you don't have a structure of the global Feynman diagram when you just look at the action. You only have the rules for building them. So that's why, I mean, well, now I'm not a mathematician, so I'm not totally sure how you would classify them and check.
Sorry, but since unlike you, we doesn't stop at some finite end, right? You want to take the continuum limit.
Yes.
But then really the set of measures zero, they're just gone for good.
I mean, also on this continuum limit versus approximation, I'm a little bit more flexible in the sense that for me it doesn't make too much of a difference. I can even believe that in nature there is some physical discreteness, but in practice, in order to extract a lot of effective physics, you need to take a limit. In my pot of water, when I'm boiling for the pasta, there's a finite amount of water, is a finite volume, and all of that. But in order to show that there is a phase transition mathematically in my description of the system, you take the limit. Otherwise, you're not going to get non-analytic behavior with all the cutoffs in place.
Say, doesn't really matter. Even if you have like n equal to 100, and you scaling exponentially, and if you say like
No, okay.
Square, even for
No, what I'm saying is that what you really believe and what you put in your model does affect what you try to extract in the limit and what sort of effects you check for and the result of the limit. The fact that in order to see what is the effective continuum description, you better take a limit, it's a practical thing for me. It's not a fundamental, too much fundamental significance.
Alessia had a follow-up to the previous question. To follow up.
Follow up to the previous question to the same person, otherwise.
So, first regarding the motivation, so do you have any, physical understanding of the fundamental physical motivation to develop on quantum field theories and go in the direction of proof field theory? So what?
Okay, these are two questions.
Then there is a question, but
okay, let me answer the first, just because it's fresh in my memory, because I was discussing with Ivano before about that. So the way I see the problem of quantum gravity is that I try to have the basic lessons from quantum mechanics, not necessarily all the principles, the basic physical insights from quantum mechanics and the basic lessons from general relativity, and I put them together. And it seems to me that the moment you try to do that, you logically are forced to drop a number of assumptions and physical principles of usual quantum field theory on a given background, and on the other hand, of course, of classical GR without the quantum effects. Sorry? Well, we already mentioned one. We mentioned unitarity. I have no idea exactly why I should expect unitary evolution in a context in which my space-time itself and the causal structure and the temporal directions and so on are either simply not there because I don't have any isometries, I don't have any given background, or they are superposed like I would expect, even not changing degrees of freedom in a quantum theory of space-time.
To make sure or for you to construct that you feel it makes sense or doesn't have pathologies. So probability should still make sense as one.
Okay, no, wait. Then I follow the same chain of thought, and I got convinced that you also had to revise a number of aspects in the foundations of quantum mechanics, for example. And I'm interested in what could be a proper understanding of a quantum formalism, even if you keep it mathematically as it is, in a context in which space-time is dynamical and quantum and so on. And it could be some covariant consistent histories. It could be some more epistemic perspective. I don't know, but no. So this is the motivation for which I feel that we need some theory that may even go beyond just quantizing GR, because I should be flexible even with the principles of quantum mechanics, and I should be flexible with what are the degrees of freedom of my space-time theory. So that's my motivation for being okay, at least expecting or not being shocked by having to work with a formalism in which I'm trying to find out what the principles are, and I don't rely on the principles of quantum field theory as we know it, or GR as we know it on their own. Now, why specifically group field theory? Well, there are many reasons beyond the purely historical ones. I mean, personal historical ones. It's just that in fact, they're intertwined. The point is simply that I was coming from certain ways of trying to approach the problem of quantum gravity, spin foams, loop quantum gravity, lattice gravity, and so on. And I simply got convinced that in these formulas, you can try to put together lessons and mathematical structures and techniques and results from all these different ways within a framework that, although still mysterious in terms of the principles and so on, could offer additional tools, a different perspective, and so on. But it's not a physical motivation like, somehow by thinking about the synchrotron radiation from the Crab Nebula, I got the idea that it must have been a group field theory behind that.
Well, I start to hear words like propagator, continuum limit that I understand. So the question is, when you talk about propagator, you talk about the graviton. Can you see the graviton coming out from?
Again, these are two questions. What I mean when I talk about the propagator, and the second is it a graviton propagator? The answer to the second is definitely not. Not in the sense that I cannot see in principle the graviton propagator, but in the sense that the one I'm talking about has nothing to do with the graviton propagator. What I'm talking about is in this tensorial field theories, there is a kinetic part, there is a quadratic part in the action that I also use in this more or less standard perturbative Feynman expansion to glue together interaction vertices, which are the ones that come from the non-quadratic terms in the action. That's all I mean.
But you don't feel the need to connect with the perturbative gravity, the classical gravity.
I mean,
something completely different, or
I mean, I'm still sort of a physicist, so I do want to connect to that because that's the physics we know and do and love to a large extent. But the point is not, I mean, this love for physics as we know it, doesn't translate into the fact that in my definition of the theory, the ingredients have to be graviton related as such or GR related as such necessarily. Time trying to devise procedure and carry out calculations that show that you can reconstruct in some regime of the theory an effective continuum description with the gravitational dynamics there, including the perturbative dynamics that would correspond to a graviton, and even before that, gravitational waves, which seem to be also observationally more relevant, and so on. So I don't know if this answers the question.
so you can extract it.
So we can start at the moment. What we can do in this particular formalism is unfortunately something simple, just scalar inhomogeneities around cosmological backgrounds. And when I say we can do it, of course, I'm saying there are many things that are to be understood and so on. But we have equations that under a certain set of assumptions and procedures have a reasonable interpretation as describing the dynamics of scalar perturbations around the cosmological background. The tensor aspect is difficult for a number of other reasons, but they're more, I mean, there are limitations of current control over a set of observables and the dynamics of the theory. There are no in-principle limitations. If I found an in-principle limitation that prevents me from having gravitational waves perturbative around the background, I will start working on something else. Because
you will be able eventually to get gravitational wave.
I'm an optimistic person. But again, this is not a prediction. This is a hope. Of course, this is a program. If we don't get there, the field is failing. I mean, it doesn't work.
So, I mean, you will, but you're not there yet. That's what you're saying.
I hopefully will, but I'm definitely not there yet.
Okay, I think we have just one last question from Srama, right? Yeah.
Just like to know, you mentioned cosmological applications. Do you have some specific prediction coming from your approach, which can be useful in the context.
Observational prediction or prediction at the qualitative level. The fact that the well,
Even this qualitative still fine.
no, because most okay, for two reasons. Because at the level of background, the type of prediction I would strive for first would be something about dark energy. When I mentioned this, accelerated expansion, after clarifying how generic it is, and so for if there's sort of a universal type of effect, what is missing is a more precise characterization of the time scales of when exactly our the different accelerated phase of the universe starts, and how long is the intermediate Friedman like expansion. All these quantitative aspects are still not there. So the qualitative picture is there. It's reasonably robust. I can tell you all the caveats, but the quantitative picture is not there. And so we are not at the level of making a prediction about, there should be, yes, something like phantom dark energy with such and such dynamics of the equational state with this precise numbers there.
On principles, can phantom of energy fit there because phantom scalar is.
Say it again, sorry, I couldn't hear.
How phantom scalar can fit in the framework and basically phantom scalar comes to the wrong sign of time, so it's. If you take it as effective time, but fundamentally.
Yeah, the difficulty. Yeah, the difficulty. I'm not a cosmologist, but from my discussion with cosmologists, the ones to whom I asked for help, the main missing aspect is that most of the distance scales and quantitative things had to do with the light propagation in the universe. It's in terms of that they determine the time frame of different epochs and so on. And that requires that we also control that type of perturbations in our universe, and we extract them from the fundamental theory, because we're not at the level of effective field theory in which we add an electromagnetic field, or we have a manifold with a metric and we look for geodesics. I mean, we are not there. We have to reconstruct all of that structure, and that is missing. That's for the background. Most of the predictions in cosmology have to do with the cosmological perturbations, though, like CMB and so on. And for that, again, there are two aspects which are missing that I can think of on top of my head. One is a proper determination from quantum gravity principles, I mean, within the framework of a vacuum for the perturbations. Because somehow that is definitely not the vacuum of the theory, because the theory lives on a different Hilbert space and so on. But somehow there should be an effective quantum description of even of scalar perturbations, and we should be able to determine what is the relevant effective vacuum for the quantization of that. And we are not yet there. And the other thing, well, lacking that, we have also issues with writing down a cosmological spectrum for the perturbations. We have a dynamics. We have an effective equation that we can compare with GR, and I can tell you what works and what doesn't. But we don't really have the full quantum field theory story with the spectrum and so on. Again, it's not a matter of principle, it's a practical thing. I don't yet know how to do that, how to answer that question. And therefore, I cannot go to a cosmologist and say, this is the number that you should observe there.
Okay, cool, fantastic. So I think time is over and we can go for lunch, but let's thank again Faye and Daniela